This video looks at an idea called convergence. Um, and before we get into convergence, I just want to take a little bit of a take a little bit of time to talk about some notation writing, and then we'll get into convergence. So I've got all the odd numbers written here and all the even numbers written below. And how would I express all the odd numbers using our idea of n? Well, if I wanted to write these odd numbers, I could say that f of n, sorry, not f as a function of n, which we write as a sub n, would equal, well, I want to somehow increment by go by 2 each time. So n needs to be doubling, but I want to make sure that it's odd. So the way that we could write that is 2n, and that'll make sure that I increase by 1. And um, then I'm going to put a minus 1 here. And we could put plus 1 as long as we have our counting the right way. So if we were thinking about this in terms of a series and adding these, I would say summing it up. Well, I need to start at 1. So what would n be to have to start at 1? Well, n would equal 1 going to infinity. And just to see how that works, when n equals 1, we have 2, 1, minus 1, and that equals 1. And then 2, 2 minus 1, that equals 3. And 2, 3 minus 1, that would equal 5. So this notation is often used if I want to get odd numbers. Whereas if I want to get even numbers, I don't need that minus 1. I can just put 2n, and I'm summing it from n equals 1 to infinity. And when n is 1, I get 2. N is 2, I get 4, 3, 6. And that ensures getting even numbers. Why I do this? Well, I want to take a second, again, before we get into convergence, to look back at some things we learned about in the last video when we were learning about series for the first time, and we were talking about how could I write these 3 major functions in series notations. And these functions, e to the x, sine x, and cosine x, are going to be used a ton over the next chapter. And what we were able to do to get these, well, remember we had to write the idea that we could approximate any function as a polynomial function, and that polynomial approximation was f of 0 plus f prime of 0 x plus f double prime of 0 x squared 2 factorial plus f triple prime of 0 x cubed 3 factorial. Remember that. And we generated these series for e to the x, sine x, and cosine x. And what I've done over on the right is summarize that in my sigma notation. So e to the x is simple. We're just increasing the x powers by 1. So that's why we just have x to the n. And then, I've got 2 factorial, 3 factorial, 4 factorial. So we're just going up by n factorials. And sine x is a little bit tricky because we're only looking at odd degrees. 1, 3, 5, 7, and I'm going negative, positive, negative, positive. So to deal with that negative, positive, I've got this negative 1 to the n. And we looked at that before. All that does is, when n is an even number, we get positive. When n is an odd number, we get negative. And then I want to get odd degrees, so I have this 2 to the n plus 1. There, in the last slide, we had minus 1, but we started with n equals 1. Or you could put 2n plus 1 and start your counter at n equals 0. And on the bottom, we've got the factorials. Again, they're odd factorials, so we have this 2n plus 1 to get odd factorials. And similarly with cosine x. So just wanted to throw these up because these were developed and we sort of increased our development to them now. We're going to be using these throughout the next couple of videos and throughout the homework assignments. Okay, so let's just review. Moving on. What is convergence? Sorry, we're not quite there yet. So, more review. General form for all power series. Uh, Again, this is review. This power series is when we centered around x equals 0, but then the generalized form for centered around x equals c, my power series is right here. And so the main thing to just recognize that is that it's a string of polynomials from 0th degree all the way up to the nth degree. We have some coefficient, and then we're always going to have x minus c. So the idea is what we're looking at is for what values does does our series converge to a single number? And it's the same idea of convergence and divergence that we looked at in chapter 10, only now we're adding the idea of series notation. So we've got this function, and right away you should notice, oh, this is clearly a power series, and we want to know for what values of x is it going to converge or diverge. It's a power series. Just to write out the first couple of terms so you see them, we'd have a to the 0 plus a to the 1, x to the 1 plus a to the 2, x to the 2, dot, 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 dot. We don't need that to answer this question, though. We want to know for what values of x does a series converge or diverge? Well, you know that a power series converges when r is less than 1, or when the absolute value of r is less than 1. And our r value here is x. So this is going to converge when the absolute value of x is less than 1, or when x is between 1 and 1. So these are the values. So as long as uh, x is between -1 and 1, my series up there will converge to a set number, and that's the definition of converge, to go to a set number. And what will it converge to? Well, just as a reminder, it will converge to, well, in general, it converges to um, a naught over 1 minus r, where r is x. So it's going to converge to a naught 1 minus x. So for all values of x that are in this interval, this series is going to converge to a sub 0 over 1 minus x for values of x between -1 and 1. What values of x does this following power series converge to, and what is its sum? So again, same idea, only now we're talking about we get a specific a value. Now we know a is 1. So we could write this as 1 times x to the n. And using the same idea, because our rate, our multiplier is still x, we need x to be less than 1 for it to converge. So as long as x, or I'm writing for x in between 1 and -1, the series is going to converge to 1, because that's my initial value, over 1 minus x. So now I know I can I know what that infinite series converges to, given a domain restriction on x. So this is the idea of convergence. We want to know what value does it go to, and what needs to happen, what must be true about x for it to reach that value. Well, there's an important test that we're going to be using a lot called the ratio test. And what the ratio test looks at is whether or not something is going to converge or not converge. So what we're looking at in this ratio test is we're looking at some term, the nth term, and then the term right after that, the n plus 1th term. And we want to say, okay, well, let's say that that approaches something. So as n gets really, really big, what does this ratio approach? It approaches some value L. For us to converge, to a value, in order for there to be convergence, to converge, we can't be adding incremental value. So for us to converge, a to the n plus 1 needs to be less than a to the n. If a to the n plus 1 was bigger than a to the n, if a to the n plus 1 was bigger than a to the n, then we would be adding substantial amount. We'd be increasing the value. But if a to the n is less than a to the n, then we're going to converge. We're getting smaller. We're not incrementally increasing. So the idea is, if we look at the ratio right here, we have the absolute values just to, because we're only looking at magnitude. If this number L is less than 1, that means that a to the n plus 1 is less than a to the n. Therefore, it converges. The series will diverge if L is greater than 1. Well, if L is greater than 1, what that implies is that my n plus 1 term is bigger than my n term, which shows that it's growing, not converging. And then the last thing is that if L equals 1, in other words, that would mean a to the n plus 1 equals a to the n. Unfortunately, we can't conclude anything there. So we can only conclude convergence if my n plus 1th term is less than my nth term. So let's look at how you can use this ratio test. So we've got this function. It's an interesting series. The sum from n equals 0 to infinity of n factorial x to the nth. And we want to know for what values of x will it converge. So we're going to use the convergence test, a to the n plus 1 over a to the n. And when we do that, we've got, well, n plus 1 factorial over, or not over, but times x to the n plus 1 all over n factorial x to the n. Okay, well, now we need to use, our understanding of factorials. We could rewrite the numerator as n plus 1 times n factorial, and then we could write that as x times x to the n. Just to make that clear, that's like x to the 1 times x to the n, which is x to the n plus 1. So divide that by n factorial x to the n, and very clearly things are going to start crossing off. So we can get rid of this, get rid of this, get rid of this, get rid of this, and what we're left with is n plus 1 times x. Now, I had omitted a pretty critical part of this ratio test, which is that there should have been in here the limit as n approaches infinity, because that's what we're looking at when n gets really, really big. So I could add it, here, here, and so the limit as n approaches infinity. So for what value will this converge? In other words, for what value of x will this be less than 1? Well, clearly, as n gets huge, n plus 1 is going to get huge. And so the only, and x stays x. So the only way that that value can be less than 1 as n approaches infinity, the only way that this can be less than 1 is if x equals 0. And if x equals 0, then the limit as n approaches infinity of n plus 1 times x will be less than 1. Therefore, it converges. And that's only true if x equals 0.